Here is the first section from chapter 11. The definition of a circle is the set of all points in a plane that are equidistant from a given point. That given point that all those points are equidistant from is called the center. And the center of a circle is at the middle. And we actually name a circle by its center. So for example, if this point at the center was P, I would name my circle P. Now a radius is a segment whose endpoints are at the center of the circle and a point on the circle. So what I have drawn here in blue is an example of a radius. Finally, a diameter is a segment that passes through the center and whose endpoints are on the circle. So what I have in green is an example of a diameter. There isn't an interior region to your circle. The interior region is all the points inside your circle. So what I've highlighted in yellow is an example of the interior region. And obviously the exterior region would be all the points on the outside of your circle. If you need a moment to copy down these definitions, pause this video and restart when you're ready. The next section talks about lines and segments that intersect circles. One special segment is a chord. It's a segment whose endpoints lie on the circle. So what I've drawn here is segment AB, and that's an example of a chord. And thinking back to the previous slide, a diameter is a special chord that goes through the center. A diameter also has endpoints that lie on the circle, just goes through the center. The second important, now this is a line, is the secant. It's a line that intersects a circle at 2 points. And the key word here is line. So a secant is never going to be a segment. So line CD is an example of a secant. Finally, I have a tangent. It's a line in the same plane as the circle that intersects the circle at exactly 1 point. So what I've drawn here, let's call it line EF. Line EF is an example of a tangent. And that 1 point that it intersects the circle at, I'm going to call H. Point H is called the point of tangency. It's that point where the tangent and the circle intersect. Now what I want you to do, pause this video, read example 1, and answer and give the most descriptive name for parts A through D. So you should have gotten segment AD to be a diameter. The most descriptive name is a diameter. Another accurate name would also be a chord, because it is a segment whose endpoints are on the circle, but this is a special chord that goes through the center, hence a diameter. CD. The best name for this one is a radius. Both endpoints, well, one endpoint's at the center, one is on the circle. Now for part C, I'm asking about line EG. Well, line EG only intersects that circle at 1 point, so it's a tangent. And finally, HB. Notice the notation they have on HB. They're talking about segment HB. So only that blue piece. Because it is a segment and not a line, this is going to be a chord. We also have pairs of circles, so relationship with pairs of circles. Circles are congruent when their radii are congruent. And one thing I want to make note of, when you're talking about more than one radius, we do use radii, not radiuses. Concentric circles. A pair of concentric circles, that's when you have two circles that have a common center. Or in other words, they share a center. So it almost is going to look like a dartboard. So here's the common center, which I'll do in green that they both share. And both of those circles are concentric. And finally, I have tangent circles. Tangent circles are circles that intersect at exactly one point. There are two types of tangent circles. They could be internally tangent, where one circle is inside the other intersecting at only one point, or they could be externally tangent, where the circles do not overlap, one is not inside the other, but they still intersect at only one point. Now, keeping with the same theme of external and internal, we do have different types of tangents. So this picture on the left, this is an example of common external tangents. Line L and line M both intersect the circles at exactly one point, but they're on the outside of both circles. Now the difference between this picture for common external tangents and common internal is lines P and Q. They both intersect each circle at one point, but they go in between the two circles. So they go through the space in between the two circles on the inside. Now we have more tangent lines and points of tangency. Now these two theorems are going to be a big factor on the next page with our examples. If the line is tangent to a circle, then that line is perpendicular to the radius drawn to that point of tangency. So if we look at this picture on the top right, I do have line AB. It is a tangent line, and its point of tangency is P. Well, I drew a radius to point P, and that radius and tangent line are perpendicular, so they form a right angle. So line AB is perpendicular to segment OP. We also have the converse. If the line in the plane of a circle is perpendicular to a radius at its endpoint on the circle, then that line is considered tangent to the circle. So we can determine if a line is considered a tangent line by, if I draw a radius to that point, does it form a right angle? And that will tell us if line AB is tangent or not. Let's go to our last page. Given circle O with tangent PQ. So I am telling you PQ is a tangent. When I draw a radius to that point of tangency, I do form a right angle. By using that theorem on the front page, we actually already answered example 2. The measure of angle OPQ is 90 degrees, so it's a right angle. Example 3. Given circle O with tangents PQ and QR, find the value of x. Pause this video, solve for x for example 3, and write an equation. Now that you've finished example 3, we know that this blue figure, ORQP, is a quadrilateral. All the angles in a quadrilateral have to add up to 360 degrees. Well, they're telling us that one angle is considered x, another one is 120 degrees. What about these two? Well, because I have two radii drawn to points of tangency, I know they're both going to be right angles. So when I add those together, 90 plus 90 is 180. When you solve for x, you should have gotten 60. Example 4. For example 4, we do have to take parts A and B separately. So I'm going to do part A in blue and part B in a different color. For part A, they're asking, is UT a tangent? Or if UT is a tangent, find the value of x. So they're telling us that UT is a tangent. Because they are telling us that information, I know that that's going to form a right angle with my radius. Well, I do have a right triangle, and the complementary angles, the acute angles in a right triangle, so the 37 degrees and the x, are going to add up to 90 degrees. And I can get for x 53. Now part B I'm going to do in red. They're telling me, instead for part B, that x is 55 degrees. And I have to figure out if UT is a tangent. Well, if UT is a tangent, I would make a right angle. Well, let's see. If UT is truly a tangent and it does form a right angle, 37 and 55 should add up to 90 because they would be the acute angles, and acute angles in a right triangle adds 90. But that's not the case. So because I don't have a right angle right there, UT is not a tangent. So it does not form a right angle with my radius. Example 5. Pause this video and solve example 5. If PQ is truly a tangent, we don't know this yet, but it would form a right angle with the radius and the tangent line. So we need to see if that blue figure is truly a right triangle. Now when I give you all three sides to see if a triangle is right, we use Pythagorean theorem to test. So if this is truly a right triangle, 5 squared plus 12 squared should equal 14 squared. Well, when I simplify the left, I get 169, and on the right, I get 196. Those two are not equal to each other. Because they are not equal, it is not a right triangle, it does not form a right angle, and PQ is not a tangent. Here's the last part for our notes. Even more tangent lines and points of tangency. If two segments are tangent to a circle from the same external point, then the segments are congruent. So if I look at the picture on the left, I am telling you that SR and RT are tangent to circle Q. Well, because both of those are tangent and they are both drawn from the same external point R, so point R is forming both of those tangents, I can assume that segment SR and RT are congruent. Now, using that idea in example 7, pause this video and find the length of AB. So for example 7, I have the same external point A that is drawn or creating 2 points of tangency for line AD and AB. Well, because I have two tangents drawn from the same external point, AD and AB are going to be congruent. So in order to find the length of AB, I do have to solve for x first. And when I solve for x, I get 16. But that's not what the problem is asking for. I need to take that value for x and plug it back in to the expression for AB. And once I multiply and add, my final length for AB is 116. Make sure that you have all the notes from today's video down and ready to go when you come into class tomorrow. Make sure to have questions to ask your teacher as well. Thank you. Bye.